All right. So let's get started. Last time in class, we've sort of been introduced to the realm of things that rotate. There are there is an easy way to sort of do calculations with things that spin and rotate. In last class, I showed that maybe we don't always want to do it in Cartesian coordinates, sort of just X, Y coordinates. It becomes a hassle after a while trying to, recalculate a position vector or trying to calculate something's velocity of its spinning. Sort of prompted us to arrive at some kinematic equations for things that rotate. They looked nearly identical to the linear kinematic equations that we've known for so long, all the way back since chapter 2. These kinematic equations are for constant angular acceleration. And that's sort of right where I stopped in yesterday's class. Let me go just that one extra step more, and I'll just sort of relate the linear world to this rotational reference frame, or these tangential like velocity to angular velocity. How do you go from one to the other? So let's start there. Okay, so they look very similar. How do we go from one to the other? Well, let's first look at what these, or what's a tangential velocity was like. So it's you're on a curved path, something that's moving along a curve, and so say, use my hand. Say there's the curved path. The tangential velocity is a straight line that just runs. Let me try to a straight line that is just touching one side of this path, and it continuously changes as the path changes. So it's related to where it is on this arc. So we have tangential velocity depends on where it is on the arc of this curve. And if we, instead of doing, really big chunks from here to here, going all the way around, what if we take just a small little sliver? That's what we're doing, ds over dt. Small change of arc over small change of time. Well, we know that's a small change of arc. This is from yesterday's class. Small change of this arc length is related to its distance away from its point of rotation. So r, so radius of this arc, times that is a theta. So d theta, that's the change in angle. So it went from here to here. That's a change of angle. And I use the radius. This is still over time. Those two things, radius times change of angle, that was sort of shown a bit more in last class. Let me, from this point, well, let's just take that radius out. Radius is going to be constant throughout something spinning. If something spins, we're following the same point on an object. as it spins and the point is not moving relative to the object, that will be a constant radius. So let's take that constant value out and let's leave the rest of this fraction. And from here, we might see that there is a change of angle over change of time, or a small sliver of angle, small sliver of time. That is just the angular velocity. So we have this relationship that we've arrived at. This is v sub t. So that's just tangential velocity. R omega. So this is just looks like a W. So tangential velocity to angular velocity. Okay. So that doesn't look like an expression that's too bad. It's just the radius of this arc that you're moving through and the velocity that you're moving along this arc, sort of in this curved path, not the tangential path. What about the acceleration? Okay, similar sort of thing. We have this tangential acceleration. If we have this curved path, and it'd be related to the velocity is, let me try to, there we go. So you can see it. Tangential velocity is just a straight line going straight up. If the point is right here, my wrist, it'd be going straight up. That means the tangential acceleration would also be going straight up, and it's related to this velocity. Try my best to make this look like a sub. This is v sub t, not v times t. So we have this small sliver of velocity over a small sliver of time. Up here, we've just solved for tangential velocity. Let's write down what what we've arrived at. We have this radius, which is now just a small sliver of angular velocity over a small sliver of time. So ultimately, we have this tangential acceleration is just the radius times the angular acceleration. Tangential acceleration to angular acceleration. All right. We have this relationship. We have the kinematic equations from yesterday. We're sort of building up a dictionary so we can use things that we are already familiar with some rotation problems. What's sort of this next step? If we think back to what was the next step from chapter 2, we did forces and then also energy kind of about the same time. So we're going to look at let me shrink this down just a bit. We're going to look at the rotational kinetic energy. From the sort of linear kinematics, we had the basic equation. You should all know this very well by now. That is K equals 1/2 mass times velocity squared. Your book calls it just K. I've seen it as KE. I've also seen it as T. I'll just leave it as a capital K. It's also the symbol for the energy doesn't change when it goes to a rotational point of view. For many objects, when we were doing something that's linear, it was just adding up all of the individual small kinetic energies. So let me kind of show that. So we have this kinetic energy is a summation. So we're just adding up all of the small pieces of this MI squared. So this basically, this is saying 1/2 M1V1 squared plus 1/2 M2V2 squared, so on and so on, until we've done all of the things that we're doing, or accounted for all of the objects. Let's take this equation and put in what we know, or what I've just sort of figured out above with rotational velocity. So I'm going to put in the rotational velocity for this down here. Here, we'll keep it like this frame. So we'll have, well, this 1/2, that's a constant value. Let's take it out of the parentheses. It's going to be multiplied by everything. So it's fair to take it out. 1/2 1/2 summation of these however many masses, and now we have this. It looks a bit more intimidating. We have to do this for every single term or every single object that we have. So maybe we can simplify this a bit. Let me take this and go one more step. I'll say 1/2, and I'm going to make a large parentheses. We'll say summation of some object's mass times the distance from its, the radius from its axis of rotation. And you can see I've done pretty much nothing different in these two equations. I've just shifted some parentheses around. What I'm doing is I want to take this thing in the parentheses. I'm going to say, I'm just going to make it a star like that. I'm going to say, let's call this thing I've put in the parentheses, let's call that something new. Let's say, let's say, try to write legibly. Let's say, or let's call that equation that I've blocked out the moment of inertia. And the symbol that we'll use for this, we'll just say capital I. For the axis of rotation. All right. So again, to clarify, I'll just say I equals what I have up there. Nothing new. Pretty much the mass of the object multiplied by how far away the object is from the point of rotation. So mass of the object times how far away it is from the axis of rotation. So the kinetic energy is just 1/2 times the moment of inertia of whatever system or object you're looking at, times the angular velocity squared. You might think this just makes it more complicated. I'm hiding a lot in this variable. I'm saying I'm just putting another equation inside of an equation doesn't make it necessarily easy to deal with. But maybe we can easily find out what these moments of inertia are for specific objects. Maybe we could sort of make a list, and that way we don't have to do this calculation every time. We just say, oh, it's this arrangement, or it's this type of system. That's easy. Oh, I've already figured that out. I already have this value. You can just use the value instead of doing the calculation over again. So let's try to figure out how to find these moments of inertia. And what exactly is it? What is a moment of inertia? Moment of inertia is somewhat similar. Like this. Moment of inertia is similar to way back when I was talking about linear inertia. All objects with mass have inertia. Inertia is just sort of the willingness for a mass to change its current velocity. So if something has a large inertia, it resists changing in velocity. If it has small inertia, it changes velocity very quickly. That was in the linear sense. So left, right, up, down, some sort of vector in a straight line. What about things that rotate? We found out that there is a rotational inertia also. This is how easily something can begin to spin. Since different objects may spin in different ways. If I have a water bottle like this, I could spin it along this axis, or I could spin it along this axis, or various other shapes. I have a book. I think you get the point. There's many different ways I can spin the same object. So there needs to be this sort of classification of this object's inertia. That's why we get in moment of inertia. Every object has its own unique moment of inertia. It's related to the shape of the object, and it's related to how shape of the object and how it is rotating. So I would say for this water bottle, I'm spinning it like this. The The axis of rotation is going straight through the center of the water bottle as I spin it like that. If I spin the water bottle like this, I'd say the axis of rotation is cutting through the middle perpendicular like that. Can you see it? So this, just imagine like I shove a pole all the way through it and spin it like that on this sort of axis. So it's related to the shape and it's related to where the axis is. So maybe we can start creating this catalog. There's a lot of stuff that can change on a single object. I don't want to have to calculate all of these moments of inertia every time I do some calculations. So maybe I can find this the moment of inertia, something spinning like this, and then save that for later. Make a list, a catalog. How do we start doing this though? Let's start with a very simple example. We're going to estimate the moment of inertia of a thin uniform rod with length L and mass M. And in this problem, we're going to try to break up the rod. We're going to try to split it up into 3 equal point masses. So I have this picture down below. Let me go like that. Okay, I have this picture down below, and currently this is a difficult problem because it's one solid object. The sort of instructions are saying try breaking it up into 3 point masses. That'll make it a lot easier. So I'm going to break this up into 3 equal segments. I'm going to try to make it equal best I can. Right there, one right there. That's pretty good. So I'm going to take each of these segments, and I'm going to take all of the mass that's in this section. Imagine I squish it all down into one single point, 1 point mass. That'll be right where the center of mass is. We'll say that's right in the middle. This is the problem also clarifies thin uniform density. Things with uniform density typically have the center of mass in the middle. So we have this center mass of this piece is right in the middle here. Center mass of the second piece right there. The third piece over here. So now, instead of this solid object that is made of many thousands of particles, hundreds of thousands, millions of particles, I'm compressing it all into just 1, 2, 3 point masses. Much easier to estimate with right now. Okay, start out with saying some of the facts about this. We have this rod right here is a length L. Okay, L. Total length is L. And the total mass is M. I'm breaking it up into 3 equal segments though, so I could reliably say, also since it's a uniform density rod, say that first one over here is just 1/3 of the mass. Second one is another 1/3 of the mass. And the third one is another third. All right. Why do I have this other line right here? Well, that's what we're rotating this object around. So imagine this is sort of like a ruler, and you've are rotating it around one end, so right where the 0 on the ruler is. So if this is the axis, it's rotating around it like that. Okay. So let's start out by writing this moment of inertia equation that we already know. I try to keep this neat looking. I equals the summation of all of the masses we're given and the distance these masses are from the axis of rotation. So it's another thing that I haven't quite labeled yet on this picture. This mass is right here, is a different distance away from the axis of rotation as that second mass. So let's label these distances also. I'm going to say this distance right here, we'll just say 1/6 L. So why 1/6 the total length? Imagine, let me sort of reason out this. If we have this dot right in the center of each of these thirds, that will make 6 equal segments. 1, 2, 3, 4, 5, 6. So hopefully you could then maybe see, take all of these lines away. That will only be 1/6 away from this axis of rotation. If we go to this one out here, that will be 3/6, the total length, L. And this final one, or I guess this third one over here, will be 5/6. And I'm measuring all of these from the same axis of rotation right here. So they're all spinning around this line right here. So they're all just circling around like that. Imagine this is a side view, perfectly side view, spinning. Okay. Back to the equations. We have this summation of each mass. So let's write out sort of how this equation would look in full. The moment of inertia is m1 r1 squared plus m2 r2 squared plus m3 r3 squared. All right, we have all of the components for this. So let's go ahead and do it, the calculation. Equals, for that first one, 1/3 the total mass. It is a distance 1/6 from the axis of rotation. Let me want to also axis of rotation. Just add that just because. Okay, so that's the first one. Second one, same exact mass, different distance away. And the third one, same exact mass, another different distance away from the axis of rotation. I'm not going to do all of the intermediate steps here. I'm going to say we get a value of 35 over 108. And the value, I wasn't given a specific mass or length, so those terms remain. So it's mass times length squared. So that is the moment of inertia that I'm estimating. So I'll say our estimation using 3 point masses. Okay. This can be good. This is a good estimation. But you will have to agree at some point that it's not representing the whole picture, right? So on this example that I'm doing, I'm just squishing a lot of particles down into a point where they're not technically positioned. This object, this solid, uniformly thin rod with length L, mass M, is not 3 point masses. There's not all the mass here, all the mass here, all the mass here. It's a continuous object. You might know where this is going. For anything that is continuous, we're going to need to integrate over some sort of range. So let me put that down here at the bottom. For a continuous object, I'll just sort of underline it like that. We'll have to do some kind of integration. So it'll be some sort of integral of how far the object is from the axis of rotation and how much mass there is. Okay. So we've done sort of this summation using point masses. Let's try to do the same exact problem, but maybe a bit more accurately. Maybe including, all of these small individual particles here. Maybe also including the particles here and just a little bit right there. This solid object's made of millions of particles. So I want to get a more accurate result by including all of them. Let's do this example. Same exact problem, except we're going to do it slightly different. We have this thin uniform rod of length L, mass M, same exact thing. I've made it look kind of three-dimensional. Maybe that would help. It's going to be rotating around one end. It's going to be rotating like around this. Spinning around and around and around. And I want to find the moment of inertia of this object. Okay, well, we have this object. We'll say that's the y-axis, and we'll have the x-axis go sort of cutting straight through the middle of the rod. This is exact same sort of setup as the previous example. Same exact thing. The rod itself is a length of L. Okay, it's going to be, let me move this up. It's going to be rotating around like that. And we want to use a different method. So instead of this, this is also, so keep in mind, this is a perfectly good way to find moment of inertia if you do have point masses somewhere, maybe a solid object that's, or a particle you could assume is a point mass. This is a perfectly good method. But instead of using this, let's try. So I'll just say try. This new form. So what I have in this equation right here is the exact same thing as above. But on our coordinate system right here, I have, let's sort of examine this a bit more. Well, we have this, object moving the x-axis. It's extending in the x-axis. So I'm just going to rewrite the equation like this to fit the picture. Okay, so let's take a little sliver of this object. So let's cut a little slice out of this object. And I'm going to look at it. So we have this slice. Just kind of make it look three-dimensional. I'm going to cut this slice out, and it's going to be a small, fraction. And I'm going to be adding up all of these small slivers together. So this sort of slice that I'm doing, that is dx. And whatever distance from the axis of rotation, that is just x. I could say r, but I'll just keep it as x for right now. Okay. This object's made of stuff. We need to determine what is in this shaded region here. It's made of many individual pieces of mass. So we have this small sliver of mass that I'm looking at with this small sliver of distance. So I have mass and I have a distance. So we have, this is related to the total mass over the total length times this small sliver of distance. So I'm just saying that, let me make the relation down here, saying that dm, this small sliver of mass, is just it's made of a linear density. So density in 3 dimensions, it's mass over volume. For linear density, we have this lambda, which is, we'll say dx, and this linear density is mass over length times dx. All right, so let's put all that we've got. We've only got this sort of new piece. Let's put that in the equation above. Squared dm, and that is x squared lambda dx. That is x squared m over L dx. And since the total mass, total length, those are constant values, this object's not changing its shape. I could take those out of the integral. Now we have this integration that is of the same variable. I've been forgetting to add the range of this. So it's right around here where we need to start considering the range. So this isn't an indefinite integral. It is from 0, right here, the axis of rotation, all the way to L. From 0 to L. Okay. Try to keep everything in frame. So we have a not too bad integration to do here. We have mass over length. That becomes 1/3 x cubed, 0 to L. And that becomes mass over length times 1/3 times L cubed. Ultimately, we've figured out that the actual moment of inertia of a thin uniform rod of length L, mass M, is 1/3 mass times length squared. We've arrived at this and we're confident with this value because we're including all of the individual small little segments as we sort of add to it as we move all the way down this total length, L. How does this compare to our estimation from earlier? So this is 1/3 ml squared. What is 1/3 in decimal form? This is easy to sort of see. It's about 0.3333, and it goes on forever. What was the, let's go like this, value of our other example, or our estimation? 35 over 108. Go like that. What is that in a decimal value? Well, I've already done this. And that fraction, 0.323. to 4, and it goes on a bit more. But you see it's very close to what the actual value is. So that's why I was saying earlier, this is still a good method to estimate. However, it doesn't include all of the small pieces of your object. Yeah, I think I'll leave that there. Okay, so we have that compared to that compared to that. You might think this is sort of a pain having to do this for this example. Took a while, took a bit of reasoning, just a bit of integration. It's nothing you should worry about because people have already gotten to this problem and they've made their own catalog of what things, what specific shapes have, what their moments of inertia are. So we've sort of already done this calculation, already seen it works for various examples. We've sort of made a list. So let me put the list up on the screen for a bit and I'll talk about it. So moments of inertia, you see how much I can't really zoom in too much because I'll just leave it like that. So people have arrived at this problem before and sort of cataloged a list of moments of inertia. So it depends on the shape of the object and it depends on where the axis of rotation is. So you look at the things on the left here. If you look at all of these over here, actually I should only say these top ones. They're all going straight through the object, through the center. So this water bottle spinning just like this. They have a different moment of inertia if it cuts through perpendicular to this object, like these. So that's for the water bottle that's tumbling like this. You see the example we've done already down here. A thin rod spinning around one side. What if this thin rod, what if it was just spinning in the middle? What if I placed the axis right in the middle and it was just sort of twirling in the middle? Well, we have this right here. Let me zoom in a bit and we'll go a bit more detailed. So for these first few, there are, imagine it's a shape that has just very minimal material that makes a cylinder right here. If you have any sort of width to this, cylinder edge, you're going to have to use something like this. You're gonna have to consider both of the radii. So from the center to, looking at this example, the center to one edge, the center to the outer edge. That will increase how much it will affect the moment of inertia. As we sort of increase this value or sort of make it more, make that hole in the middle smaller and smaller and smaller until it's a solid. Let's go like let's go like that. There we go. It's smaller, smaller, smaller. We get the sort of a large, very a large cylinder with a specific radius. We need to take that radius into account when this thing is spinning. You could look down here at these two. See that they are almost identical, except one is a very beefy cylinder. It's very large. One is we've described it as a thin rod. So imagine something very minuscule, like a coat hanger wire. A wire itself. It's a very uniform thin rod. Has the same exact term on the end here. And then we have a sphere, and we have a hollow sphere, and just a general sort of rectangular shape. How do we arrive at all of these values, though? We've done this example, but how do you go from this to something like this? We need to change this axis of rotation. If you sort of see in your head what we were doing last time, we were doing an integral, and we had the range 0 to L. If we have this axis of rotation right here in the middle, what would the range be? It would be negative L over 2 all the way to positive L over 2. And this integral would cancel itself out and just result in 0. So how do we actually get this term? Let's figure it out. In order to get it, we use something called the parallel axis theorem. We can use this for those shapes that we've just worked on. We could also use this for, we'd also use it for just some very obscure shape. Something that doesn't match up with that chart I was just talking about. Say we have a shape that looks something like this, and we have a pole sticking through it, and we want to spin this object around this pole. Okay, so how do we manage? Okay, so the object is going to spin around this axis here. And it's going to have some moment of inertia around this axis. We'll just say, I'll just put the I sort of right here. Something that we should take a note of is this object might be off center a bit. Maybe it is, maybe this axis is right at the center mass, but for sake of the example, I'm going to say, what if the center mass is right here? That's kind of what it looks like. This is a really weird, imagine this is a weird cut of sheet metal. Center mass would maybe be kind of right here. So what is the distance between the axis of rotation that it is spinning on versus where the center of mass is? So what is the distance here? From here to here. We'll call that h. Ooh, I'll just put that. I don't like that. That makes it better. Okay. Parallel axis theorem is an equation that helps us out a lot. It says that we have some obscure unknown moment of inertia, I. That'll be equal to moment of inertia if it were rotating around the center of mass plus the total mass of the object times the distance it is away from this actual center of mass squared. We'll say mass m. This point right here is the center of mass. And I believe that's it for this picture. Okay. This is a bit vague. Let's jump into the problem that we've been doing this whole time. Let me go back to this uniform thin rod with length L, mass M. Okay. Let's do this example one more time. I'm just going to go like that. I'll rewrite this stuff, or I'll peek back up at the top when we need it. So this example, again, I'll uniform thin rod. Length L, mass M. Okay, let's draw a little picture of this scenario again. Sort of an exact side view. I don't want to make a 3D picture at the moment. Something like that. There's our uniform thin rod with length L. Let's go like this. 0 to L. What is the object's center of mass? Well, since I say this thing is uniform density, things with uniform density typically have the center of mass in the center of the object. So center of mass is right here. Okay. Let's mark that out with a sort of large dotted line. So this is going to be a dotted line. I'm just going to erase a bit of this. Okay. What's the distance from the origin? So 0. Again, I said that's probably about halfway. In this case, it's exactly half since it's uniform. Well, we found the moment of inertia when it was spinning around this axis before, right? So we found that value. So in this case, I I'll just say I is the moment of inertia. Let me rewrite the parallel axis theorem so sort of you could see what I'm talking about. So it was I equals I center mass plus mh squared. Now you can see I is the moment of inertia from its current axis of rotation. And its current axis of rotation in this picture I'm drawing is right here. Right on the very end. We've already done this problem before. We already know this value. Okay, I'm just gonna call that y. This is x, just to clarify. Now, what else do we need? What is I center of mass? So the moment of inertia center of mass is the moment of inertia if it were to rotate from its center of mass. Okay, and I will say, I'll just sort of underline the if it were part. If it were to rotate. That's the whole thing, sure. So that means if it were to rotate around this dotted line I've drew. Okay, maybe we already know that, maybe we don't know that. In this case, we don't know that value. We want to actually solve that at this point. So we have that equation. Parallel axis theorem comes to the rescue. We know one moment of inertia, and we don't quite know what the moment of inertia is if we were to rotate it from the center. Because again, remember that integral, if we went negative L, we went negative L over 2 to L over 2, doing an integral like this, you see you have one term subtracting the exact same thing, it would cancel itself out. That's sort of why parallel axis theorem is being used right now. Plus mh squared. Okay, I'm going to say, I'm going to call this right here, I'm just going to say I, y. So that's about the y-axis. Okay. This turns into me solving for the moment of inertia from the center of mass. Okay. So we already have pretty much most of this expression. My center of mass is the moment of inertia from one end. We've already found this. So I'll say 1/3 ml squared. That would be IY minus m times h squared. What is h? H is how far away the center of mass is from its current point of rotation. So that's L over 2. Squared. We get moment of inertia of something about a uniform thin rod, length L, mass m. Moment of inertia about center mass is 1/12 ml squared. And if we take that result that we've got, specifically using the parallel axis theorem, that was the reason we were able to find this. Specifically using that, we go back. We see that is what it is on the chart. So the parallel axis theorem is something that will help us out in switching places of where something might rotate around, switching where the axis of rotation is. As long as we know one, we can work our way out. As long as we calculate for one, we can maybe work our way out from there. Okay. Then I'll leave it on this for a minute. For an obscure object like this, it would be a matter of breaking it up into manageable pieces. You could do point masses to get a very good estimate. Break it up into sections. Say there's a point mass here, here. Then you think about if you break it up to a lot more point masses, you get a little bit more accurate. A lot more point masses, a little more accurate. If you're able to describe this shape with a function or something, you'd be able to then integrate over this exact shape. Once you have the shape, you could then do plenty of things for that type of object. But what we're trying to do with these moments of inertia is say how easy is it for this object to rotate. Let me that's a good point. Let me go back real quick to that page. So all of these moments of inertia tell me how easy this object is to spin about that axis. The larger the moment of inertia, that means it's going to want to stay the way it is currently. So the larger moment of inertia, the larger resistance to start and stop. Smaller, that means it's easier to start and stop spinning. Okay, I think I'll leave it here for now. The next little bit is torque. I don't want to add torque onto the end of this lecture, so I'll start out with torque tomorrow. I think, yeah, we're gonna definitely finish this chapter tomorrow. We'll move on to angular momentum. Chapter 10. We're going to get the homework updated to have some questions on rotation. So for our upcoming quiz. Other than that, if you guys have questions, let me know. If not, I hope you have a great day. I'll see you later.